Hello everyone, welcome to the session number 11 on NumPy as part of the training program on Introduction to Python Programming and its applications in water resources sector. NumPy or numerical Python is a fundamental package for scientific computing in Python. It lies at the heart of many Python data science libraries such as Pandas and other third-party packages useful for handling data. So we thought of keeping a separate session on NumPy covering the basics before going ahead with covering the session on how to handle raster data using Python. Let us recollect what we had done. We started with the basics of Python programming in the first 6 sessions, and then we introduced you to Pandas, which is a versatile Python library for data analysis and manipulation. It is used for handling the tabular data. Pandas comes with two data structures, Pandas data frame and Pandas series. And we had seen the GeoPandas third-party package, which helps in handling the vector data. GeoPandas is nothing but an extension of Pandas with an element of geometry added to it in the form of a new geometry column. So it is similar to the Pandas with it also has two data structures, Geo data frame and Geo series. And we had seen that GeoPandas has dependencies on Shapely and other Python libraries and packages. Shapely package, we had seen that it provides for geometry objects like point object, multi-point object, line string, multi-line string, polygon, multi-polygon. These Shapely geometry objects, they are not associated with any coordinate reference system. So, and then we had seen how to read data from a CSV file and how to create a pandas data frame and how to generate a geo data frame and then how to write the data from a geo data frame into a shapefile. We had seen two functions read underscore file, to underscore file, which are the which support a variety of formats, not just shapefile but even the geo package, geo database. So let us now go ahead and cover the basics of NumPy in this session. We are aware of two types of data models in geographical information systems, the vector data models and raster data models, which are used to represent the real world objects. Vector data models, we have seen the points, lines, and polygon objects, which are which have sharp boundaries between them. Whereas in case if any parameter varies spatially in a continuous manner, such a parameter is better represented in raster data format. For example, all hydrological parameters associated with the hydrological cycle, whether it is rainfall or whether it is soil moisture or whether it is evapotranspiration, all the such data, all such parameter um, are better represented in raster data format, which are stored are captured in square tiles as square tiles in where the data is stored as numerical array of rows and columns, and therefore it is a two-dimensional array. So raster data sets are stored as numerical arrays of rows and columns with each pixel representing the space and the value of the parameter. For example, if you take the digital elevation model, you have each pixel associated with its location, latitude and longitude, as well as the value of the elevation associated with that location. Similarly, if it is a satellite image which has been if a satellite sensor captures the reflectance in any band, single band of electromagnetic spectrum radiation, and if the captured reflectance is stored in that pixel, and if it is a processed product like ET evapotranspiration can be calculated as using surface energy balance models. So each pixel will be having a value of evapotranspiration associated with that pixel. So in that case we have two-dimensional numerical arrays. When we have multispectral imagery, or when we have more than one band, then these multiple arrays of the same size, which are called bands, um, are collected together, and this collection of the bands become a three-dimensional array, with the third dimension being the number associated with the band indexing. Unlike in case of other indexing in Python, band indexing here in the case of raster data files, it starts with 1. So you have a series of bands of same size put together, one uh, after another in like a stack, it representing a three-dimensional array containing data, with each band being a two-dimensional array of rows and columns. So while for vector data it is enough to know the spatial reference system, uh, the vector data is stored in form of vertices with the spatial data, so coordinates are known. For raster data, you need to know the pixel size, the coordinates of the horizon, and the amount by which the data set is rotated. That is affine transformation we call. They are needed to determine the rest of the coordinates. Um, so if we know the horizon, or if you consider the top left most corner as the origin, and if you know the size of the pixel, and if you know the orientation of this array, you can calculate the coordinates of the remaining points. Coming to the NumPy module of Python, NumPy, which is a short form of numerical Python, it is an open source fundamental package for scientific computing with Python. It lies at the heart of many Python libraries or packages for data science. For example, we have seen the pandas and geopandas, and we have also seen visualization through matplotlib, some examples. So other than that, the data exploration, there are other packages for data modeling, data evaluation. They most and almost all of them, they are, at their heart lies NumPy, which make they all of them make use of NumPy functionalities. When we see some of the functionalities of the NumPy, you will realize that we have already used them in the case of pandas and geopandas. NumPy, as said, it lies at the core of the rich ecosystem of data science libraries. Then when we are talking of raster data, what we said is raster data is represented in a numerical arrays, two-dimensional if it is single band, or multi-dimensional 3D array in case of multi-spectral data, raster data set. Now, to handle the such raster data sets in the form of numerical arrays, NumPy module will be very handy, as it efficiently deals with numerical arrays, and it deals with them in a faster way than the inbuilt Python data structures. Further, we have said that NumPy is designed for processing large arrays of data and therefore useful for handling raster data sets. Now, at the core of NumPy is the ND array object, which stands for n-dimensional array object, which encapsulates the n-dimensional arrays of homogeneous data types, with many operations being performed in compiled code for performance. Now, what it means is ND arrays, the data is stored in NumPy. The data is stored in the form of n-dimensional arrays, which have same data type. Elements are of same data type. Therefore, the size of the size remains the same. Unlike in the case of Python built-in sequences, where you keep adding elements of different data types, the size keeps changing, and then the code is performed in a compiled code for performance. So it combines the best of both Python language as well as the compiled code, the C code in the background. Now what, even if you are giving the inputs in the form of Python sequences, they are converted to NumPy arrays before processing, and then the results are also displayed sometimes in the as NumPy arrays. Now, the utility of NumPy arrays when it comes to one thing is size and another thing is performance fastness is it is because many mathematical operations they can be conducted in using NumPy arrays through simple vectorization instead of writing complicated instead of iterating over the elements of built-in Python sequences using complicated nested for loops if and else statements. No, the main differences between NumPy arrays and standard Python sequences are NumPy arrays have a fixed size at the time of creation, and unlike the Python built-in sequences, the elements in them are to be of same data type, therefore they have the same size, and they facilitate advanced mathematical and other operations on large numbers of data. A plethora of growing of scientific and mathematical Python packages are using them. With NumPy arrays, the code is more concise and easier to read and resembles standard mathematical notation. For example, if there are two arrays of same size, A and B, and if you want to do simple sum or product, element by element operation can be conducted in NumPy simply by writing A plus B or A into B, as in the case of normal mathematical notation, which is not the case when it comes to Python inbuilt sequences. You have to loop over the elements, you have to write for loops, and you have to write conditional. If there is any requirement of conditional statements, they will also come. So this simple vectorization with that the code is much concise, whereas in case of Python normal built-in sequences, the code would be littered with inefficient and difficult to read for loops. As such, the logic wise there is nothing wrong, but whenever you are dealing with big data, large arrays, as it happens in case of raster analysis, when in case if you are having multi spectral multi-dimensional arrays, stack of many two-dimensional arrays, when we have to do operations, when you write when you go by standard built-in sequences of Python, they occupy much space, and also the for loops they consume much of the memory as well as the computational power, so the process will become slower. um, Maybe the difference may be in matter of few milliseconds to seconds, but when with the quantum of the data increasing, you will realize that ND arrays are more efficient. Now let us see some examples of NumPy module in the Jupyter Notebook. I have initiated the Jupyter Notebook from my Anaconda prompt. You can also do it from Anaconda Navigator after selecting the environment. Activating the environment python-wrm, you can launch Jupyter Notebook. In your command prompt also, you can run the command conda activate python-wrm, and then you can type Jupyter Notebook to launch um, Jupyter Notebook. Then as usual, a default window will open up pointing to the home directory. You open you create a new Jupyter Notebook and save it, rename and save it. So I have created a new notebook. Now to start with, I have to import the NumPy module, and by convention NumPy module is imported into the script by typing import NumPy as np, a short form for NumPy. So so the NumPy node module has been imported. Now first we will see how we create uh, how do we create NumPy arrays, n-dimensional arrays. Now it can be simply created by passing a list, uh, a Python list, say list 1. I define two lists, 1, 4, and then list 2 is 5, 6, 7, 8. So if I pass a list into an np dot array, you can check by tab completion what are all options you have. So np dot array, and then you pass on the list, say list 1, you type a. So an array has been created with the elements 1, 2, 3, 4. Now let us check its shape, which is a tuple. It is a one-dimensional array and of 4 elements, so it is written in this fashion shape. Let us check its dimension with this attribute ndim, and dim stands for dimension. It should return 1 because it has only one dimension. There is only one row and one sequence we have. Then you can check its data type with this attribute a.dtype, which is int 32. So NumPy has various ways of a variety of data types: int 32, int 64, int 16, int 8, etc. For conserving memory and making calculations faster. You need not get into that, but you must know that you can even specify the type of data type at the declaration of at the time of creating the array itself. Now let us create a two-dimensional array by passing two lists, np.array which are list 1 comma list 2, list of lists. So you type b, which is a two-dimensional array I have created using these two lists, and you can again check the attributes of shape 2 by 4, 2 rows and 4 columns, then the dimension ndim, which is 2, and then the data type, which is again int 32. Then you can create let us also create another list 3 is equal to, let us create a list of floats, 9.0, 10.0, 11.0 and 12.0. Okay, then let us create a array by passing list 1, list 2 and list 3 in list of lists. and you type C. So you can see that when you are passing a list of floats, it has I think the let us check its data type, c.d type. It's float 64, as we have passed a list of floats to create a, and then is it the dimension, let's check the dimension, c.ndim. It is again, actually it's not a 3-dimension, it's a 2-dimensional only. We are only passing list of lists in both the cases. Here also we have passed list of lists, because here just the shape has been changed. You can check c.shape, which is 3, 4, 3 rows and 4 columns. Let us try to create a 3-dimensional array. Uh, Instead of passing any lists or predefined data, we have a simple option by you can use this method np dot, you press tab and check for arrange, and you can look in the help options. It is a built-in function, arrange, in module numpy. It returns evenly spaced values within a given interval. With the non-integer step we also can give, which is optional. Well, if you don't give the default start value, it is 0, and the step size, default size is 1. So it returns an ND array of evenly spaced values. So let us check. Say there are examples, np.arrange 3, it is exclusive 3. It creates an array of 3 elements, 1-dimensional array, 0, 1, 2. Similarly, if it is a float, then it creates a float array of floats. If you are giving starting index as well as end, then it will exclusive of 7, it creates an array. And if you are even providing the step, it will create an array 3 and 5. 7 is exclusive. So we can also, like, let us check. Let us create an n-dimensional, 1-dimensional array by passing 12. So this is an array including from 0 to 11, excluding 12. You can check the type. We haven't specified. We can assign it to D, and then you can print D, and then you can check D dot D type, which is int 32. Now we have said that at the time of definition itself we can specify the so let us, D is equal to np dot arrange 12, then you can change the data type by simply using the function d dot as type. You can check d dot as type and use the help option. Which says as you can see here, an array of floats is converted into array of integers. So let us see d dot as type in brackets. You can float say 32. So you have created an array by changing the data type. So you can define an array with the specified data type at the beginning itself. You can define it this way. Float 64. Sorry, and you have to say np.array. D type is, you can specify, and you have to use the strings. Yeah, and then you can type E, which is you can check the type float 64. So this way you can create an array using by passing a list of lists, or by using the arrange function, and then you can reshape any array, existing array, to create a new array of a different shape. So you can create a new array and reshape. You can say it of dimension of shape 2, 3, 4. 2 first dimension, second dimension, third dimension. That is in each of the ND array there will be two components having blocks having 3 rows and 4 columns, and the number of elements are 24. 2 into 3 into 4 is 24. Yes. So let us see. Yes, this is an 3-dimensional array where which has two two-dimensional arrays are put together to create a 3-dimensional array. You can check its shape, which returns a tuple 2, 3, 4, and then you can check its dimension, which is 3. And so we can also create arrays, ND arrays, by using simple functions, inbuilt functions like np.zeros. By giving the shape, like say you specify the shape 2 by 2 or 2 by 3, which has to be passed inside the brackets as a separate tuple. So a 2-dimensional 2 by 2, 2 columns and 2 rows array has been created. You can assign it to any variable. Similarly, np.once will pass the same shape, yeah, different shape, 2 rows and 3 columns. It's 2-dimensional array. Then np.empty, say again 2 by 3, it creates an array. It doesn't create, like in case of list, it will not result in an empty list, but it puts some garbage value, and which can be reassigned again and again. Say np dot, let us say 2 by 4. So yeah, because in memory there was this has been there, it is simply giving. So you can see np.empty 2 by 4 array, which is a 2-dimensional array of 2 rows and 4 columns. It has put some garbage values. and then you can assign the values. Now for assigning the values, you should be able to identify the how you should be able to access the elements. Now how do you access the elements? Let us see. Let us get back to the first array, which is one dimensional. This one we have in the beginning we have seen, and we can access any element by passing within the square brackets, say first number. Again, indexing starts from 0, so first element, it is as if it is a list. It behaves in the same fashion. And similarly, you can zero, 2, 3, exclusive of 3, it will print 0, 1, 2, 3, exclusive of the index 3. So it gives an one-dimensional array subset of this. Then you can have, this is a two-dimensional array. Now if I want to access the first row of this, which will be a n-dimensional one-dimensional array, you can simply pass on the index 0, which is array 1, 2, 3, 4. Similarly, you can access any column, say 0, 1, 2. Okay. Comma 2. Yeah. You can simply pass index, row index, but you cannot simply pass the column index. You have to pass for selecting all elements of the row. You can pass simply colon, then comma, then second, the third column, that is index 2. You can pass, and then you will get the array 3, 7. Similarly, the slicing and subsetting of arrays, you have similar options as we had seen in earlier. Say I want everything excluding the first row, the first the second row, which is of index 1, but however columns, I only want these two columns, these two. So that means indexing 1, 2, 3 excluding. So 1, 3. It should get me 6, 7. Yes. So it is now this array, what do you think is the dimension of this array? It is a two-dimensional array. So we can access a two-dimensional slice from a two-dimensional array by stating the ending and starting and ending indices of both the dimensions. We have seen till now how to subset, how to get contiguous values by subsetting. But we can also get discontiguous values by the same order you pass. We have A is an one-dimensional array, and with its elements at index 0 is 1 and element at index 3 is 4. If I want 4 and 1 in that order, you can simply pass list of lists with indices 4, 3, 0, which will give me an array, and one-dimensional array with elements at index 3 and element at index 0. You have the B, which is a two-dimensional array, and if I want if I pass list of lists like 0 comma 0 comma 1 comma 0 comma 1 comma 3, let us say. Yeah. So here what I am again passing a list of lists, 0 0 1 0 2 3. It actually gives me the elements corresponding to the index 0 0, row 0 and column 0, which is 1, then row 0, then column 2, that is 3, then row 1, column 3, that is 8. So this way, if an array is multi-dimensional, you can provide list of lists with inner list for each dimension. Then one important thing is mutability of ND arrays. Now, if you are subsetting any ND array and make changes in that subset, the original array also gets the change is also reflected in the original array. So to preserve the values, you have to make an independent copy explicitly. For example, you have this B, the two-dimensional array, and now I will take a subset by getting the elements 2, 3, and 6, 7. I will pass on. Let me call if G is equal to B, then 0 row, both the rows I would like to have elements, then first and second, 1 colon 3 exclusive, which will give me a two-dimensional array with the elements 2, 3, and 6, 7. So if I make an assignment, the first element by double index notation is also valid here. That is, if I am changing this element 2 to say 9, then if I print G, naturally the assignment you will see the changed value in G 9367. However, the same even in B, which is its superset of G, it is being reflected. So to preserve the values, you need to make an independent copy. Now, if two or more arrays have the same dimensions, then we can perform mathematical operations and as well as logical operations on them, element by element wise, which we have spoken in the initial slides. That is an advantage offered by NumPy arrays. So, for example, let us define two new arrays, x two-dimensional arrays. X is 3 4 np dot array. So x is a 2 by 2 two-dimensional np array, 2D array, and then I will also define y of the same dimension. So I have two-dimensional arrays x and y defined. Now I can perform simple mathematical operations, arithmetic operations x plus y simply by using this notation x plus y, which will do the element wise addition. You can see 1 minus 1 is 0, 2 plus 3 is 5, 3 plus 4 7, 4 plus 3 7. Similarly, you can perform x minus y, then x into y, even product minus 1, 6, 12, and 1 into minus 1, 2 into 3, 3 into 4, 4 into 3. So you have this array. So this is very useful when it comes to band map algebra, band mathematics, which we will see when we want to identify any features like water body or even vegetation. We have indices and we have band mathematics we have to do, where if the bands are of same size, which is the case in where when we have multispectral images with different bands and you want to do manipulation with bands, you can simply use such operators to calculate indices so as to identify the features on the earth as per the, like NDVI is used for identification of vegetation, greenness, and then NDWI, normalized difference water index, for identification of water bodies. So that way, so, not just arithmetic operations, mathematical operations, we can even do logical operations. For example, you can try with this x greater than y. So it will result in an array with the corresponding elements are compared. Like 1 is greater than minus 1, it is true. Then 2 greater than 3 is false. Then 3 greater than 4 is false. 4 greater than 3 is true. False, true. So you have this Boolean array, and you can assign it to any say h is equal to x greater than y. You run it again, and then you can print h, and then you can check h dot d type, which will be a Boolean d type bool. So you can do that, and you can even combine the conditional operators by using and, which is ampersand, and then or operators, just as in the case of pandas, which we have seen. Now, if you want mathematical matrix algebra to be implemented instead of such element-wise product, then you have to use numpy dot linear algebra submodule, and numpy dot linalg submodule has to be used. Now we are not concerned about that matrices. We are talking only about simple numpy functionalities. Then this comparison operator, this can be used to implement if-else statements in NumPy. Like you can see npy.where np.where you have the expression conditional x greater than y, and you can print, if it is true you can print corresponding value as 1, and if it is false you can print the corresponding value as 0, or you can print the if it is true you print 10, if it is false you print 20. Now you can see wherever there is true, the corresponding elements are 10. So if statement, the conditional statement, then implement this, else you put this value. False, corresponding elements have the value 20. So this is like an if-else statement. This can be even be operated with two arrays in the place as values, instead of giving specific values, provided those arrays are of the same size. For example, you take a simple I equal to np dot zeros, and you specify the dimension j equal to np dot ones, and you specify the dimension. Sorry. Now you can implement this statement, np dot where x greater than y, then instead of 10 you pass I, instead of 20 you pass j. So what happens is, for corresponding values of this boolean array, for true, if it is true, it takes the corresponding value from I. If it is false, it takes the corresponding value from j, array j. So you will because it is true, false, false, true, it has to be, you will get an identity matrix 1 0 0 1. Let us check. 0 1 1 0. Wait a minute. Yeah, because I is zeros, np dot zeros, and j is np dot ones. You will get zeros in place where so how it executes is, it checks the condition x greater than y. So first element, first row, first column, it is true, therefore it has to take value from I. The corresponding value in I is 0, it will place 0. It is false, then it has to take the value from j. The corresponding value from j is 1, so it will take 1, so forth. So that is about Boolean indexing, which will be useful. Then we will we should talk about something called Nand values masking. Suppose you say you have an A is an array, and let me assign the first value to 0. So A becomes array 0 2 3 4. Let me divide each element by 0 and see what happens. It is throwing a warning division by 0. However, what is more, I want to point out that whenever you are dividing 0 by 0, it will give an in nan. It will provide an value of nan, and whenever you are dividing any integer divided by 0, it will provide inf. If it is negative, it will be minus inf, I guess. Otherwise it is inf. So this you should know. Then talking of masking, whenever you have numpy arrays, you can subset with corresponding boolean arrays for extracting and modifying some of the values in an array, only with those values which correspond to the true value. Suppose there are missing values, you know the locations of those missing values, and you want to avoid them in your calculation. You can mask them out. You can do the calculation, and then once you do the complete the operation, you can assign any no data value to that those missing values. Like by convention, people assign very large negative values, minus 9999. So that can be done. So by using the once you mask the arrays, you can completely ignore certain pixels in the calculation, so that they will not interfere in the calculation, and you do your calculation, and then you can fill with no data value afterwards. So that that will be useful, especially when talking of raster and band math and raster analysis. And also, if suppose A, now it is an array. Now suppose I assign one value at index 3 is 100. So A will be changed. Now this is an outlier value. Suppose if I want to remove that, you can simply if you want to exclude such values, you can simply use the operations like a less than, say, only 10, some threshold value. It will generate an array of only those elements, removing the outliers. Similarly, if there are missing values, you can replace those missing values with average values of the surrounding pixels. So many things can be they are possible. We are not getting much into the those details. Then summarizing array values, when you have an array, you like a, now it is, the values are such that now if you apply the sum operation, it will it is same as np dot sum. You will get summation of all elements, and a dot max, you will get the maximum element, and a dot min, you will get the minimum one, 0. So this is summary. This is very simple because it is one dimensional. Suppose you have two dimensional array, say b, which is this is two dimensional, and you want the sum along the axis. There are two axes in two dimensional. One is along the columns across the rows, which is axis 0, and along the rows across the columns axis 1, the same thing which we had seen earlier, where in case of data frames that had the basis in numpy itself. Pandas had a dependability of numpy, but we haven't dealt with numpy in the beginning. But now we are dealing with it because we want to use it for you want to have understanding of element by element operations for doing raster analysis. So array, if you have this two-dimensional array, if I want b dot sum along the axis, you can specify the axis is equal to 0. It will return, sorry, it should be b. It should return an array with summation along the columns: 1 plus 5, 9 plus 6, 3 plus 7, 4 plus 8. Then you can do the same thing along the axis 1, along the rows, where then you will get 1 plus 9 plus 3 plus 4, which is 17, then 5 plus 6 plus 7 plus 8, 26. That is about when similarly the same, if you want to find out the maximum, m dot max axis equal to 0. So maximum, it should be 5, 9, 7, 8, and you can check it. Do we have a three-dimensional array? No, this is also two-dimensional. Let us define C as a three-dimensional array. np dot array simply 1, 2, 3, 4. can check C, which is and the dimension of C, which is a 3 dimension, and shape of C, which is 2 by 2 by 4. There are two along axis 0, two elements, and number of rows in each of the array sub array. We have 2 rows and 4 columns, 2 by 2 by 4. So this is the array, three-dimensional array C defined. Now if I want to simply check the maximum values along the C dot max, say along axis 0. Axis 0 now is you can imagine this as a two-dimensional array, and this is another two-dimensional array which is on the top of this, two layers, two bands, and your axis 0 is perpendicular to the surface of each two-dimensional array. So if you check that, it will simply give you row and column summaries, the cell maximum comparing corresponding elements. Like 1 and 9 will be compared, 2 and 10 will be compared, 3 and 11 will be compared, 4 and 12 will be compared, and you will get the same dimension array. In fact, you will get this as the final output. So you have the two-dimensional array of, because the maximum of any element here and corresponding element is 9. So that is when you do this operation along the axis 0, you get row column summaries. And if you do it along the axis, say axis is 1 comma 2, which you have to pass in a tuple. So 1 comma 2, axis 1 is along the columns, along the columns, yes, in a plane. Along the columns you have axis 1 and axis 2 along the rows, and axis 0 is perpendicular to the plane of the each two-dimensional array. So if we are checking for C dot max along the axis 1 as well as 1 and 2, that means you will get layer wise or band wise maximum values. So in this layer the maximum is 8, in this maximum is 16. Now let us do this for axis 0 and 2. That means along the rows in the plane and across the perpendicular to the plane. So that should give me we are considering when we considered 1 comma 2, it gave me layer max. When I am considering layer and row, I should get column max. So column max, let us see, 12, 16. Axis 0, which is perpendicular, then 1 is along the column and 2 is along the rows. So you will compare this row and this row along 0 and 2, that maximum is 12, and this row and this row the maximum is 16. Now do that, let us do that for axis uh, 0 and 1. Now that is 0 means layer, this is one layer, this is another layer, and 1 is across the along the columns. So then you will get this as the maximum. Yes, so you will get the column maximum. So in that way you can similarly you can do the sum along the axis. Now that is not much of relevance to us for the time being. Now we can we talked about no data values. The missing data, uh, suppose you have the array A is this much. Suppose A of 3, it is none. You cannot define none. Yeah, because in an array these are numerical, only numerical values are allowed. So to represent in NumPy, the representation is np dot nan. Cannot convert float nan to integer. Okay. See, a dot d type it is int 32. That is the issue. Actually the np.nan, it can only be accommodated in float arrays. So let us convert it into a dot as type float 32, then you assign a 3 is equal to np dot nan cannot convert float nan to integer. You have to assign it to a. Okay, then can we do this? Let us see, because nan np.nan is only accommodated in float arrays. Yes. So you have the nan value, there is a missing value which is represented by nan. So whenever you have the nan, you operate nan np.nan with any other integer or with any other thing, the result will be nan. For example, you can see a dot sum. Now it will because one of the element is nan, it will return nan. To get, in order to get the, if you want to ignore that nan and get the sum of remaining elements, you can pass on this function nan sum, a dot nan sum. No, you have to, np.nansum is the function and you have to pass a inside the attribute. So 3 plus 2 plus 0, it is 5.0. So that way, so no data values can be ignored using special functions such as nansum, nan. Similarly, there are other functions which will ignore the no data values. No data values, we can find out the no data values using this function np dot isNan, and you can pass on a. So only one element it will return true, others are not nans. So these are useful for masking out the elements which are missing your nan values. As we said earlier, you can simply mask out the elements which you want to avoid in your calculations, and then do the operation, and then assign no data value to those specific cells. So there are much more. NumPy is a very it has versatile applications in various data libraries, but we as we said in the beginning, we our point of concentration is only up to this. We have learnt about how to create NumPy arrays and how to do the math, how to slice get elements, subset the arrays and get any element or slices, and how to do element by element operations using simple mathematical and logical operators can be used for simple operations element by element. And we have seen the Boolean indexing, which can be used to mask out values, and masking will be used to remove the missing values from any operation. And we have seen 0 by 0 division will give you np.nan, and any integer divided by 0 will give you np.inf, which are to be avoided when we are doing band math. And then finally summation using these functions dot sum dot max along the axis that we have seen. So let us move forward. Let us work with another package for dealing with raster data, that is Rasterio. So let us see some examples of handling raster data. We will make use of a third-party package Rasterio that we have installed on first day using Conda installer. Rasterio. We will only see basic examples. We will see how to read raster data, how to read it as a Numpy array, and whether we can make use of the functionalities of Numpy array that we have seen to do band math, some mathematical operations on Numpy array. We will just try to explore the very basics. And you can further go to the website of Rasterio and then check the documentation and the examples provided over there, and you can run them on your Jupyter notebook by making suitable modifications. As we have been saying, this training program is only meant is meant to be a foundational program or introductory program. Geospatial analysis is not actually part of the scope of this training program. However, we would like you to be aware of various third-party packages which are available for doing data analysis and geospatial analysis. So let us start. Rasterio is based upon GDAL, which is a geospatial data abstraction library which is written in C++. It is a popular and robust library for reading and writing raster data. However, because it is it is in a different language, and the way you have been coding from the beginning, the way you have seen a very intuitive, very easier and elegant syntax. So to carry it forward, the Rasterio third-party package has been designed, which internally it works on GDAL. On the back end, GDAL it only works to read and write data. However, the interface it won't be much. It is much easier to deal with raster data using Rasterio. Now let us see. So I have clipped the DEM, SRTM DEM of 30-meter resolution for Pune region, and I have saved it on my system. So the clipped DEM file, I have saved it in this file in data folder as srtm underscore Pune underscore region. Now let us try to open this file and read the data as numpy array. I will create a heading. First of all, you have to import the Rasterio third-party package into the Python's into your script using this command import Rasterio. Along with that, I will also import other useful modules which are part of the standard Python library for file handling and file path handling, like path lib. Then I can use OS, then import glob. I may or may not make use of all these modules. However, I am importing all of them. Then I have to define a file path to my srtm dm clipped file, which is stored in my system. I will initiate it with pathlib.path.home, which will point out to the home directory. And then I have the folder python wrm and subfolder data wherein my file is saved. So I will use the forward operator, / operator, and I will define the file path python wrm, then data, the name of the file, .tif. You can check what has been created, fp underscore dem, which has created an Windows path to the file and the srtm dem clipped file. Then in Rasterio there are functions for opening and reading raster data files. You can check them by typing period and then press tab. There is an open function. You can use help option to read about what the function does. So it is a help on function, open in module Rasterio. It takes file path and other parameters are optional. The default mode is read mode. It returns a dataset reader or dataset writer object to open a GeoTIFF for reading using standard driver discovery and no directives. You have the example scripts. So we can then, because now we have the file path defined, you can simply pass it to rasterio.open. which creates a dataset reader object. You can assign it to a variable DEM, and then you can check the type of DEM, which is rasterio.io.datasetReader. Now you have opened the file. Now before reading the data, let us check the metadata of this raster data file. You can make use of the attribute meta, dm.meta, So you can see the metadata related to this file. The driver is GOTIF, which means the format, the raster data format. Then the data type is integer 16. Here the values of the elevation are stored in the as integers. Then no data, none. Width 6711, height 5626. It is a the number of rows are 6711, and the number of columns, no, number of rows are 5626, and number of columns are 6711. The count is 1, which means there is only one band here. As such, there are no bands. There are elevation values stored in the grid. Then the coordinate reference system EPSG 4326, which is the WGS 84 datum. Then the transform, which has the left topmost coordinates of x and y, which are 73.34 and 19.41 longitude and latitude. And then the pixel size, which is in degrees, you can convert, and it will come out to be around 30 meters. 1 degree is approximately 110 kilometers. So you can multiply by 100. Then in kilometers, from kilometers to meters, you can multiply by 1000. It is around, it will come around 30 meters. So that is about the metadata. You can access these properties, individual properties, by calling the attributes like dem.driver GOTIF, then dem.height, dem.width, dem.crs, EPSG 4326, then dem.bounds. This is the bounding box which has defined within which your the SRTM your raster data file values are there. So you have the coordinates of latitude and longitude of the leftmost left longitude, and right side rightmost value of y, and then the x value varies between 17.89 degree north latitude and 19.41 degree north latitude. So that is about various attributes of your raster data file, which you have read, which you have opened using the rasterio.open function. Then we can try to read the values in the file, in the raster data file. You can name and variable elevations. Then DEM is your file, which raster data file, which was in the read mode, which you have opened. Dot read. Because there is only one band, you will pass on the band number 1. So here what we have done is, initially we have used rasterio.open function to open the file. It has just opened the file and read the properties, the raster data properties. It hasn't read any data. Now we are using the dot read function to read the values by passing on the band and storing them in the variable in the defined variable of elevations. You can check the type of elevations now, which you will find it to be a NumPy array. Yes. So now the data has been read, the raster data has been read into a NumPy array, n-dimensional array. You can check the shape of this array. by the attribute dot shape, which you will find the number of rows 5626 height, then the number of columns 6711, which is the width of the your file, raster data file. Now similarly you can check the dimension and attribute, which will be 2. It is a two-dimensional array. You can also check the values, a summary of the values which are in this two-dimensional array, by passing on dot max. The maximum value, elevation value in this in that SRTM DM file is 1483 meters. Then you can also get the mean value, which should be around 600 meters, as the region is around Pune. Yes, it is around 606.61. And you can check the minimum value. It is minus 13. It may be some one pixel may be having a local depression, or it may be a wrong value. Anyway, there will be some pixels where which may not be having the representative value. That doesn't matter much. So you can check the median value also, np.median elevation. You can pass on the numpy array elevations, which is 608 meters. So that is how you can check the values which are stored in your raster data set, by reading it as a numpy array, and you can check the values using numpy the numpy functionalities. You can also plot your raster data set inside your Jupyter notebook for visualization purpose. So from Rasterio, in Rasterio there is a sub module called plot. From rasterio.plot there is an function show, which you can import. You can check the help option, rasterio.plot.show. It displays a raster or raster band using the matplotlib. So behind the scene, the matplotlib is this is working while you call this function rasterio.plot.show. So you can visualize it, as you have already imported the function show. You can simply pass on your numpy array inside your inside the function, which should plot the DEM. You can visualize the DEM. You can also plot a histogram, which will be useful, as you can see how many pixels are falling which range of the elevations. So there is another function in rasterio.plot submodule. From rasterio.plot import show hist. Again, it is basically a matplotlib functionality which is running behind the scene. So from rasterio.plot import show underscore hist, and then you can pass the numpy array. Because you have only one band, there is no issue. So you can simply pass one parameter, elevations. Otherwise you have to specify the band number also. So show underscore elevation, show underscore hist, then you pass on the numpy array, which is elevations. Then it generates a histogram where you can find that majority of the pixels, around 1.55 into 10 power 7 pixels, are in the range 600 to 800 meters. That was a simple introduction to Rasterio third-party Python package for handling of raster data. We have only seen how to open raster data files and how to read raster data files as numpy arrays. We have earlier seen how to deal with numpy arrays when we looked at numpy module. That was sufficient. That is sufficient enough to carry out various arithmetic and logical operations on numpy arrays. So you can have a look at Rasterio documentation, and you can start working. You can download multispectral satellite imagery. Today we have only dealt with SRTM DM, where we have only elevation values, whereas in Landsat 8 and Sentinel-2 multispectral satellite imagery, we have you can download when you download and you click for any region of interest, you will have access to the values of reflectance captured in various bands, and which and in popular in the literature, that many indices are defined for identification of earth features by doing the band math. For example, the popular normalized difference vegetation index uses NIR and red band reflectance values to do the normalized difference NIR minus red by NIR plus red. That will generate a new raster data set of NDVI, provided you take care of the no data values and zero division, etc. The issues. Then you will have an NDVI data set. Uh, Similarly, you can generate normalized difference vegetation water index for making use of green and NIR bands. Uh, you can map the water bodies, and then you can convert the raster data set to vector data set and calculate even the areas of the water body. So you can there are numerous other ways where you can start working with the basic information that has been provided to you. You can make use of rainfall data sets, which are raster data, graded data sets. If they are daily rainfall data sets, you can do the summation and you can generate monthly rainfall data sets. And from monthly rainfall data sets, you can do the summation to generate annual rainfall data set. Because each data set is read as a numpy array, you can do simple summation. In the next session on geospatial analysis using Python, working with raster data, you will see how to work with raster data using GDAL library.